Please be seated. I open this public session of the Council of Deans of the Vrije Universiteit Amsterdam by affirming that, from the Christian origins to the present day, we practice science with a sense of wonder and inspired by fundamental values. Welcome, everybody, to this inaugural lecture, this event. Julia Schaumburg, she will now accept her chair in, let's see that I do this correctly, Econometric Methods and Applications, and the title of the lecture is On the Importance of Questioning Assumptions. Julia, the floor is yours.
Thank you, Arjen. Dear all, dear family and friends, dear colleagues, it's my pleasure to welcome you to my inaugural lecture today. I'm so happy to see you all here in the still young year of 2026. The title of this talk is On the Importance of Questioning Assumptions. I submitted this title 2 months ago, long before I had started even thinking about the exact contents of this lecture. When a good friend asked me what the lecture would be about, I told her the title, because that's all I had. And she said, in a quite disarming way, but entirely correct, great title choice. This way you can say almost anything you want. So here I am. In the next 35 minutes or so, I will take you on a journey of my academic career until now, which has been shaped in many ways by the question of which assumptions we can safely rely on and which ones we can no longer afford. The world is complex. In some sense, one could argue that almost everything depends on everything else. You may be familiar with the concept of the butterfly effect, the idea that something small can have unanticipated, large, even world-changing effects. However, for many decisions in everyday life, we cannot go through the whole chain of possible cause and effect. That's why assumptions are very useful. For example, in traffic, a common assumption is that fellow drivers follow the rules of stopping at red and going at green. This works almost all of the time. So coordination is simple, and as a traffic participant, we don't have to negotiate at every intersection. Even when traffic lights malfunction, it is reasonable enough to adjust our assumptions and simply start using a rule like left yields to right. Let's abstract from Amsterdammers on bicycles for this one. My point is Risks can be mitigated because most people follow the traffic rules and assume correctly most of the time that others follow them as well. Accidents at traffic lights are rare, but more importantly, if they happen, the authorities step in. In most cases, it can be established who was at fault and measures can be taken. The damage can be contained, and there is no reason to believe that after an accident we have to question our assumptions when driving towards an intersection again. That's an example of a robust assumption. Even when it fails locally, the system itself remains intact. I started my PhD at Humboldt University Berlin in October 2008. I had done some internships before and was interested, I really was, in developing new statistical models for market risk and credit risk to later work in the risk management department of a bank or another financial institution. Before 2008, risk management was based on a central assumption that risk could be broken down into components that could be controlled separately. Even though concepts like financial contagion and bank runs were well known in academic research, in practice, regulatory authorities monitored the risk of each institution more or less in isolation, assuming a bank's stability depended primarily on its own activities and funding, plus maybe the overall state of the market. On this slide, I would like to bother you with a statistical measure of risk that is well known and still quite widely used. It's called value at risk. Technically, it's a feature of the distribution of losses and gains that a bank might face over time. It answers the question, what is the worst loss we can expect over a given time period with a chosen level of confidence? For example, if we say with 99% chance we will not lose more than 1 million euros within the next week, our 1 week value at risk is 1 million euros. And there are statistical methods to predict this number, and this year is a small example for such a model. Suppose we monitor profits and losses every day, then this model says that the value at risk, so the potential loss that will only be exceeded with a small probability, depends on the bank's profile and activities, as well as the state of the financial market. Before 2008, this was roughly what banks were required to report to regulation authorities on a regular frequency. And these then gave them requirements as to how much cash to hold to be able to balance out these potential losses once they materialized. You may remember fall 2008, or perhaps not. Some people are very young here. On September 15th, 2008, the investment bank Lehman Brothers filed for bankruptcy. This was the moment when it became clear that most assumptions about financial risk that had been used to prevent losses had failed spectacularly. To be clear, what failed was not just a model, but a way of thinking. The assumption that local safety, the safety of each institution, implied global safety, the safety of the system. What the global financial crisis revealed was that the system was, in reality, quite fragile. But this fragility did not come from only individual risk exposures, but from the dense web of interconnections between institutions. When losses began to occur, first in the subprime market in the United States, they started propagating along channels that were hidden or at least not monitored by regulators, and were therefore unaccounted in risk models. This enabled shocks on local markets and bankruptcies of individual firms to turn into global disasters. So the assumption that risks could be broken down and measured in isolation turned out to be inadequate, to put it mildly. After the crisis, it became clear that risk models had to account explicitly for the propagation of shocks for contagion. Doing so, however, is not straightforward. Interconnections between financial institutions arise through many different activities, and much of the relevant data were not systematically recorded before 2008. Even after regulators began to collect transaction-level information, the picture remained incomplete because banks operate across borders under different regimes. Resulting data sets are massive and messy, and confidentiality requirements make them largely inaccessible for transparent scientific research. And even if all connections could be fully observed, incorporating them directly into risk models would require a very high degree of complexity with questionable practical value. So this challenge was what motivated 2 chapters of my PhD thesis. In the resulting papers, my co-authors and I proposed a framework to measure a bank's systemic risk contribution, the risk it poses to the system, as if it becomes distressed, right? So that's the value at risk. Is based not only on its own characteristics, but also on its position in a network of spillovers. Crucially, we showed how such a network can be estimated using only freely available market data. And thereby, we could capture interdependence without relying on confidential transaction records. Here is the network. We estimated using about 10 years of data for the United States financial market. What you see here are the links between institutions. These little arrows that are maybe a bit hard to see. The colors indicate different types of financial firms. And in the paper also, the arrows have strengths. So some connections are thicker than others. Each arrow should be read as a risk spillover. It means that distress at one institution is systematically followed by increased risk at another one. In other words, when one bank gets into trouble, the arrow shows where the trouble is likely to travel next. We assessed the fit of the model based on this network using statistical methods, but more importantly, we also looked at individual institutions in detail to see whether the links made economic sense. For instance, when we re-estimated the network using only data from before 2007, its overall structure remained remarkably similar. Moreover, the risk rankings, or the systemic risk rankings that came out, corresponded closely to which institutions later showed the strongest distress signals during the crisis and how much damage their problems caused elsewhere in the system. Although I started working on this project in 2009 already, shortly after the beginning of my PhD, it was only published in 2015. By that time, however, it was already widely known because it was among the first models to explicitly represent how financial risk propagates through a network of interconnected institutions. In follow-up work, somehow miraculously that one was published earlier, we questioned one of our own assumptions from the earlier paper, that risk networks are essentially stable over longer periods of time. Using data from the European banking sector, we re-estimated the model year by year. And as you can see, the network in 2009, here on the right, is quite a bit denser and has more connections than the one on the left. This simple exercise already revealed that systemic risk is not static, it changes over time. And monitoring these changes in real time can be informative for regulators. As I said, though, here we simply split up the data into years and re-estimating the model separately for each subsample. While this introduces a lot of flexibility and we can see all these changes, it's not always the best thing to do. Something not visible from these plots is that each arrow we see corresponds to a component in the model that is estimated from data. And such estimates always come with statistical uncertainty. This means that because we only observe a limited amount of data, we never know the true strength of a relationship with certainty. And the arrow we draw is only our best guess within a range of plausible values. With shorter samples, this range becomes wider. So some links that appear strong may in fact be noise, while others that matter remain undetected. If we ignore this uncertainty, we create a false sense of precision, which may lead us to over-interpret patterns that are not really there. The challenge is not to abandon time variation, but to design models that allow us to track risk in real time while staying honest about how certain these estimates are. One way to address this challenge is to design models that explicitly incorporate time variation in the relationships between different variables, and let that time variation be informed by new data that becomes available at each time point as we move forward. This allows us to use longer time spans of data for estimation and then that increases the statistical reliability, still allowing for dynamics and potential instabilities. And such models are called time-varying coefficient models. And Vrije Universiteit Amsterdam happens to be one of the main academic hubs when it comes to the development and application of these very powerful models. In September 2013, I started working at the VU, in the Department of Econometrics and Operations Research. A chain of circumstances had induced me to look for postdoc positions in the Netherlands, including 2 econometric games in 2009 and 2010. And to those who want to know, we got into the finals both times. A Netherlands Econometric Study Group conference in Leuven, which I kindly got accepted to, even though I was not a Dutch or Belgian econometrician, but a German PhD student, and a wonderful research visit at the University of Tilburg upon invitation of Professor John Eymal. So I came to the VU and started as a postdoc in a European consortium grant called SURTO. What a name. Stands for Systemic Risk Tomography. I could not have wished for a better fit in many respects. First, the project was in my area of expertise, systemic risk measurement. And second, I had the chance to learn in depth about the time-varying coefficient models I mentioned earlier by working together with some of the pioneers in the field, André Lucas and Simeon Koopman. I also worked with other colleagues in the Netherlands and internationally in academia and in central banks on a variety of research projects that combined one or more of the ingredients shown here. Tails, or also risks, refers to methods that aim at modeling rare outcomes, such as extremely high losses on the stock market or extremely high changes in credit spreads. When we are interested in events that are rare but potentially very harmful, we face the challenge that our data sets, by construction, do not have so many informative observations. It might even be a bad idea to use all the available observations when we are strictly interested in the extremes. So there is an area in statistics devoted to studying extremes that, okay, maybe not entirely surprisingly, is called extreme value theory. The second aspect, interconnections, is one that you already saw in the context of my research on systemic risk. I worked on econometric models for multivariate time series data that are intrinsically connected with each other and therefore co-move. Thirdly, as I already mentioned, I worked a lot with time series data, devising models that could account for some type of instability in the relationships between 2 or more variables. These boxes shown here refer to some of the empirical applications I addressed using these methods. For example, my co-authors and I modeled credit risk contagion among countries during the European debt crisis. And we were able to provide some evidence which monetary policy interventions were actually successful in addressing the crisis and which ones were not. In another paper, we looked at co-movements among the economic sectors in different European countries, which is important for policy because it helps to quantify economic integration among the members of the Eurozone. In yet another paper, we examined what happens to the systemic risks of banks if interest rates become negative. In the years since I started since I started my postdoc at the VU in 2013, things changed considerably, not only in the world at large, but also within my immediate working environment. Data science grew as a new discipline, and machine learning, which is essentially a way to view statistical algorithms, which originates in computer science, became more and more popular, also in applied finance and economics. Even my department got a new name and became the Department of Econometrics and Data Science. And a new bachelor program of the same name started in the School of Business and Economics. The number of students we welcomed in our study programs in econometrics increased approximately by factor 3. The so-called data science revolution also had a strong influence on my research agenda. Together with PhD students and co-authors, we worked and still work on a variety of projects in which we integrate flexible components from machine learning into established time series models. Together with Andre and Bernd Schwab from the ECB, for example, we studied how bank business models change over time depending on monetary policy interventions. In another line of research, together with Siko Kuiker, PhD student, we explore how neural network models that are traditionally used in large language models or image recognition can be adapted to the properties of economic and financial time series data. Overall, I believe that the direction of bringing together modeling principles that are well understood with data-driven flexibility is a promising one. On the one hand, we can question and relax assumptions we suspect to be too rigid and build tools that are more realistic and more useful. At the same time, by controlling the amount of flexibility we introduce, we are in a better position to study the theoretical properties and limitations of these models. You may have noticed that despite the developments in my methodological toolbox, I mostly kept working on empirical applications that are broadly related to financial stability. This area was where I saw the societal contribution of my research. By analyzing complex economic and financial data with new innovative methods, I hope to better understand how risks build up over time and how crises might be prevented rather than just managed once they have already unfolded. In my projects, I collaborated with researchers from central banks and economic research institutes. I traveled extensively and attended conferences and workshops all over the world. I especially remember a conference trip to Sapporo, Japan in 2018. Scientific program was excellent, and I got useful feedback on my work. But actually more important were the cultural and social activities around the conference. Attending a Japanese whiskey tasting at 10 in the morning with colleagues from the Bank of England, or discussing a new paper idea with my friend and colleague from the Bank of Canada while sitting in a bathhouse, are just two examples of the many highlights of this trip. I think it's fair to say that I was enjoying that period of my academic life quite a lot. This lifestyle came to a complete halt in early 2020, as I'm sure you all remember. Suddenly, I did all my work on my laptop from my dinner table. No traveling, no discussions or lectures in person. No meetings with students on campus. I was lucky not to be especially vulnerable to the coronavirus, so while I had to adapt my way of living due to the new situation, I was also able to enjoy some aspects of it. Most importantly, the lockdown situation accelerated the discussion between my partner Lance and myself, as he was living and working partly in the United States and partly in Liberia, West Africa at the time. After 9 months of travel ban and working from home, Lance and his cat, who's also my cat now, Omar, came to live with me in Amsterdam. Isn't he beautiful? This is Omar. Okay. So Lance is a virologist, and he has worked for the Dutch health authority, RIVM, now for 5 years. Even though our backgrounds are very different, we started collaborating on a research paper some time ago, and it got published in 2025. This is just one example illustrating that as econometricians and data scientists, we can learn from and contribute to many empirical fields, and that our research scope can extend far beyond economics and finance. I'd like to come back to the COVID lockdown, because it made me question fundamental assumptions about the systems I grew up and lived in for almost 4 decades. Within weeks, routines that had seemed immovable before suddenly dissolved. How we work, how we travel, how we organize education. It struck me how fragile many systems turned out to be that I had never questioned before. Just think about the sudden scarcity of basic food items or toilet paper. Talking to my partner Lance, the virologist and public health professional, about this, however, revealed that I had my assumptions backwards. What I experienced as a sudden breakdown was, from a public health perspective, simply the moment when long-standing vulnerabilities became visible. In other words, the pandemic did not create fragility, it exposed it. It was impossible not to be reminded of the global financial crisis I mentioned at the beginning of this talk. In 2008, we also thought we were witnessing an extraordinary shock, only to later realize that the real problem lay in the assumptions we had been making all along. About independence, about stability, about how systems behave under stress. Once you start looking at crises this way, not as isolated accidents, but as moments when hidden vulnerabilities surface, it becomes difficult to treat the pandemic as a one-off event. Many of the forces that allowed COVID to emerge and spread so rapidly are the same forces that are driving the climate and environmental crisis. The destruction of natural habitats, the intensification of global mobility, and the growing pressure we place on ecosystems. In other words, the pandemic was a consequence of how we currently organize our relationship with the planet. It gave us a taste of what it means to live on a stressed planet. Unfortunately, or perhaps fortunately, this was not the end of my questioning of assumptions. Once I began to look more closely, it did not take long to grasp the remarkable breadth of scientific consensus that the planetary crisis is human-made and that we already know many of the pathways to address it. Of course, there are uncertainties and difficult trade-offs, and the transition to a sustainable economy will not be without costs. Not everybody will benefit. There might have to be a few less billionaires. But with the Paris Agreement in 2015, the signing governments, including the Netherlands and my home country, Germany, committed themselves not only morally, but also legally to act. Against that background, I was shocked the first time I saw this picture. It shows the steady rise of atmospheric CO2 among the warming of the planet. And it marks the moments when the world officially acknowledged the problem. The first climate conferences, the first IPCC report, Kyoto, Copenhagen, Paris. What is striking is not only that the curve keeps rising, but that it rises unaffected by these milestones. Decade after decade, the crisis was recognized, and decade after decade, the underlying trajectory continued. What to do? I'm an econometrician, not a climate scientist, not a physicist. I do not generate the fundamental evidence that underpins our understanding of the climate system. But I am also not convinced that the core problem is lack of knowledge or even lack of concern. Surveys and research studies show that many people are, in fact, quite worried about climate change and environmental degradation. The problem, it seems to me, lies elsewhere, in implementation. And the yawning gap between what we know, what we publicly acknowledge, and what actually happens. Once you start looking at this more closely, another question emerges. What are the tools academics actually have when they are convinced of a cause? Traditionally, our contribution is research and teaching. Producing evidence, refining methods, reducing uncertainty, transmitting this knowledge to our students. Beyond that, however, there's also advocacy, advising policymakers, translating findings to a broader audience. And then there are forms of protest in which we deliberately step outside institutional channels to signal urgency and failure of the status quo. Not everybody agrees with me that these latter two roles belong to scientists, and I understand. For much of my career, I believed my responsibility ended with doing careful work and clear communication, trusting that democratic institutions would take it from there. Over the past 5 years, however, as my assumptions about the pace and effectiveness of climate action began to shift, I became less certain that this division of labor holds. When evidence accumulates, concern is widespread, commitments are made, and yet outcomes remain largely unchanged, the question of responsibility starts to look different. And so with time, I ended up pursuing all three components of the puzzle. The first thing I did was join Scientist Rebellion, an international climate movement of researchers who believe that the credibility, visibility, and privilege that comes with an academic position also carry the responsibility to take the streets. at least when the scientific consensus is as broad as it is in the case of the climate and environmental emergency. I joined many actions with this group. We blocked roads to stop government subsidies to fossil fuel companies. We protested new gas drilling in the Waddenzee in front of ministries and public institutes. We communicated scientific facts about the climate and environmental crisis by putting posters in places we were not supposed to. We got arrested by the police, and then we got released again. I discussed my activist work with colleagues in my department, and even though people tended to be reluctant, understandably, to protest in this way themselves, they often agreed with the demands behind our actions. Indeed, we are in a situation where if the Paris Agreement is taken seriously and we want to limit global warming to 1.2 degrees, our remaining emission budget is very small and likely to be used up very soon. How radical is it then to disruptively but non-violently oppose drilling for gas in a World Natural Heritage Site, or to abolish tax benefits for the use of fossil fuels? Another question: how sensible is it for universities to collaborate with the fossil fuel industry when it is precisely these companies that lobby tirelessly against the transition to more sustainable energy sources? Not at all, right? Again, not everybody agrees. Perhaps that because they fear that categorical opposition to certain collaborations compromises academic freedom, or because they believe that engagement with large industry, including fossil fuel, is a pragmatic way to fund research projects which might contribute to technological progress. In an opinion piece in Trau that we published with 4 colleagues in 2022, we argued that not only have companies like Shell actively misrepresented climate science and lobbied against effective climate policy for decades, collaborating with them shapes research agendas and institutional priorities in subtle but powerful ways. Our conclusion was that maintaining such ties is incompatible with the public mission of universities, and that ending them is neither unprecedented nor radical. It follows the same logic that led universities to distance themselves from the tobacco industry once its practices became indefensible, and from Russian institutions after the invasion of Ukraine. Our opinion article was picked up by the university board of the FU. And after a campus-wide debate over several months, it was decided in April 2023 that no more research collaborations will be entered with the fossil fuel industry unless strict criteria are met. For me, this was a rare and encouraging example how questioning assumptions can translate into concrete institutional change. Not because everybody suddenly agreed, but because the conversation had become impossible to ignore. In the years since, I've been involved, together with colleagues and students, in several initiatives aimed at making the climate and environmental emergency a central theme within education across disciplines. These included dialogues with students as part of the Elephant in the Classroom campaign, as well as 2 public week-long reading marathons in the VU lobby, where staff and students were invited to read aloud from scientific literature at the intersection of climate science with all other academic fields at the FU, and to engage in an open discussion. None of these actions may seem dramatic in itself, but my hope is altogether they help to normalize the idea that this crisis is not a niche topic, but one that belongs at the heart of the university. Over time, my shift in perspective did not only affect how I engaged in general, but also the direction of my research. My empirical interests started to gravitate more towards climate and weather data. Not because I suddenly wanted to become a climate scientist, but because I realized the extent to which many of the methods I had worked with in the context of financial stability, such as interconnections, risk, time-varying coefficients, can also be used to understand the climate system better. In one recently published paper with PhD student Barang Spaniers, My colleague Eric and Dim Kumu from the Institute for Environmental Studies, we investigate changes in the persistence of warm and wet winter weather in northwestern Europe. Using quantile autoregressive models, we show that not only are winters getting warmer, but that under certain atmospheric conditions that have recently become more frequent, warm and wet spells have become more persistent. A pattern that helps explain why flooding risks have recently escalated. In another paper with PhD student Chen-Hui Wang and my colleagues Juan and Yi Song, which we just submitted to a journal last night, we propose a non-parametric framework within extreme value theory to study the persistence of extreme temperatures. In other words, not just whether heat occurs, but to what extent it tends to cluster into heat waves. Applying the method to temperature data in cities all over Europe, we find that the probability of extreme heat lasting at least 2 consecutive days has increased dramatically in recent decades, all over Europe. Both these projects will most likely have follow-ups, and there are many more aspects of climate and weather analysis that can be addressed using methods from statistics, econometrics, and data science. The results can be informative complements for the results from physical climate models. However, to be clear, I do not believe that any academic research I can publish will convince political decision makers or the broader public of the dangers of the environmental and climate breakdown. This will need other forms of engagement. I'm almost at the end. There's one thought I would like to leave you with. Based on my academic journey so far, I'm convinced that one of the most useful habits we can cultivate, both as researchers and citizens, is to be open and willing to interrogate our assumptions about the world from time to time, to notice which assumptions do no longer work, and to adjust our actions accordingly. This can take courage, and especially the last part, adjusting our actions, can feel thoroughly uncomfortable at first, but it's possible. And the amazing part, as I've learned over the years, is that we rarely have to do it on our own. And this brings me to the final part of this talk, the people who have accompanied me and then challenged me and supported me, and at crucial moments helped me question my own assumptions. I'd like to thank them. Thank you to my undergraduate professor, Carsten Tränkler at Mannheim University, whose fantastic teaching first sparked my excitement in econometrics. Thank you to Melanie Schienle and Nikolaus Hauch, my PhD supervisors. I've learned a great deal from both of them. All my co-authors. I appreciate each and every one of you very much. Without you, I would not be the researcher I am today. André Lucas. I already mentioned him repeatedly in my talk. That's because he has played such an important role throughout my last 12 years at the FU. To begin with, he was the one that hired me as a postdoc. But also we've worked together on many papers, and you trusted and supported me to become your successor as head of department. And most importantly, you've always had an open door for me. Thank you. Simeon, thank you for welcoming me in the department all these years ago. Ever since I first met you, your deep understanding of all things econometrics and your passion for research and teaching have been a constant source of inspiration. Thank you. My PhD students, past and present. Dieter, Igor, Quint, Barend, Chen-Hui, Siko, David, Mick. It has been and it is a privilege to work and a joy, important, to work with you. Thank you for trusting me as your supervisor. Dear colleagues in the EDS department, it happens often that I'm simply happy to work at the 11th floor with all of you. Thank you for the great atmosphere. It is not something to be taken for granted. And Alice, you're a big part of creating that atmosphere. Thank you. Thank you to the faculty board of SBE, to Arjen and Rob and Mirella and Fleur, for supporting my appointment to Professor of Econometric Methods and Applications, and for trusting me as head of department. Thank you to all the climate rebels here at the FU and elsewhere. Times are tough, but we're tougher. Thank you, my dear friends. Here, you make my life here and elsewhere. You make my life lighter and brighter and simply better. Thank you, Debbie and Rodney and Clara, and of course also Lulu and Rambo. I'm trying to wave at the camera, for welcoming me into your family. I'm so happy to have you in my life. It's a bit of German now. Mama und Papa. Auch wenn ich manchmal alle möglichen Dinge in Frage stelle, gibt es keinen Zweifel jemals, woher ich komme und wohin ich gehöre. Danke dafür von ganzem Herzen. Ihr seid die Allerbesten. Und ich freue mich so sehr, dass ihr heute hier seid. Lance, you've challenged many of my assumptions over the years in a unique way that combines honesty with love and unwavering support. Thank you for being in my life and for bringing Omar with you. This is the slide that should go with this. And finally, thank you to everybody for being here today, online and offline. Ik heb gezegd.
First of all, I would like to congratulate Julia with your appointment as a full professor at our school, and I would like to expand this congratulations to all your loved ones and your colleagues. Congratuleren. My German is a little bit rusty. Gefeliciteerd. My Dutch is better. Well, many things that you talked about resonate really, really well with me. So first of all, the topic, which is systemic risk, I think is extremely important. It is extremely important that we as a school also house expertise on that. You're not the only one, I understand that, but it's really at the heart of of your work, and you move from one crisis to the other, from the financial one to the climate one now. And that implies that your methods are really well equipped to kind of start to kind of analyze one crisis after the other. And personally, I'm now intrigued by another crisis, which is the crisis of democracy. Perhaps it would also be interesting to see the extent to which your methods can also be applied to political science, to see to what extent we can understand what is happening to democracies across the world, and the extent to which indeed interconnections between countries might also play a role here, for example. So perhaps we can discuss that at a later stage. I would really be intrigued to see the extent to which your methods can help us there. Your methods, that's also, of course, you're not only, you're an econometrician, you're a part of that department. Methods are very important for you and for your department. And I'm also intrigued by what you are trying to do now is that you try to link, let's say, the traditional probabilistic statistic with the machine learning algorithmic ones and see the extent to which, by combining to you, we can really, well, leap forward. And actually, I'm also really intrigued by that. And I would like also to see that this kind of things also spread, not only within the school, but also beyond to other disciplines, because by combining the two, I think we can really very much deepen our understanding of issues that relate to complexity. And this is probably also why you're interested in that, because crises are a key example of issues that are associated with complexity, but it's not the only ones. So that's another one. So another one that I'm intrigued by. Questioning assumptions. That was kind of the title of your talk. Yes, that's what we should do. Actually, I would say that is one of the kind of the defining characteristics of being a scientist to start with. questioning assumptions. I hope that we are also able to kind of teach this to our students. We need to be critical, and critical thinking is at the core of scientific thinking, and also that implies that we need to question our assumptions all the time. But there are few assumptions I would like not to question. One is that you are a great addition to the school, to our community. So we are very happy that you have joined us and that you're here now. And I do also not want to question the fact that you are an excellent scholar. And what I particularly like to emphasize here is that what I admire is this kind of really passionate, engaged scholarship. That implies that you move beyond doing only research and teaching, but try to reach out to society and engage with what's happening out there and try to contribute to finding solutions. So thank you for that, and keep that spirit. Okay, that's it. So I close this public session, the Council of Deans of the Vrije Universiteit Amsterdam, by desiring that our scientific search for truth and wisdom may be beneficial to the world and to humanity. Thank you.